Now let's look at some DFT properties. I'm not going to go over all of these that are listed in the textbook, but just a couple of them. One is the periodicity, and that's that these two sequences that are involved in the DFT, x of n, which are related to our samples of our time domain waveform, and x of r, which are related to samples of the Fourier transform of x of t. These sequences are n0 periodic, which means that these sequences repeat after n0 samples. And then some other properties that can be proven from the definition. One is the time shifting property. If the discrete Fourier transform of a shifted version of my x of n sequence, if it's shifted to the right by k, in the transform domain, that's equivalent by multiplying the x of r sequence by e to the minus j r omega 0 k. And then there's correspondingly a frequency shifting property that says we have x of n multiplied by e to the j n omega 0 m, then the corresponding discrete Fourier transform is just my frequency samples shifted to the right by m. And then the last property is periodic convolution. And this is a different type of convolution that what we've encountered in the past. Our textbook uses the notation of a P within a circle to represent periodic convolution, sometimes also called circular convolution. But when we're working with our sequences, it is the circular convolution of the two sequences. And these are periodically extended, that the discrete Fourier transform of that periodic convolution is equivalent to multiplying the discrete Fourier transforms of the two sequences. Now, periodic convolution is defined like this. It is the sum from k equals 0 to n0 minus 1 over x of k g of n minus k. So there's some similarities here with the linear convolution that we've looked at in the past. And this is a time reversed and shifted version of one of the sequences. The main difference here is the summation is over only n0 samples and not from minus infinity to infinity. Because x of n and g of n are both n0 periodic, this periodic convolution is also n0 periodic. So in the next video we'll look at using this periodic convolution to actually calculate the linear convolution, and again, that's what we're most interested in. It's the linear convolution that we get when we actually convolve the input of a system with the impulse response of the system. Another common notation that you may see that I'll mention for circular convolution or periodic convolution is this one. Okay. It's just with our normal convolution operator, an asterisk enclosed in a circle. So that's used by some textbooks, and it's a little more common than this notation, but they are equivalent.